So now we take on the transient response of series RC circuit. And here, for a change, we have taken the output voltage as the capacitor voltage, which exists when a input has been applied here. Instead of taking the current, purposely the voltage has been taken because we don't want an integral differential equation. Rather, we want a differential equation. See how we proceed. So, what is the current which will flow in this circuit? IT. What will be the relation between the voltage and the current? IT is equal to C dVc by dt. Applying KVL in this loop. Vt minus RIT minus VCT is equal to 0. Substituting for IT from equation 1. Vt is equal to RC dVc by dt plus VCT. Taking Laplace transform on both the sides. Vs is equal to RC SVCS minus VC0. This VC0 is the voltage which exists across the capacitor because of the initial charge which the capacitor possessed prior to switching on of the circuit. It means earlier this capacitor was in the circuit and it was charged. That is, the charge which was left on the capacitor after the switch was made off, that is known as, that led to the voltage VC0. So VCS is equal to Vs divided by, what should be the proper way in which we should write? SCR plus 1 plus RC VC0 divided by SCR plus 1. Taking out RC common and bringing it onto the numerator. Again here RC will get cancelled. For an RC circuit, the time constant is equal to RC. So we find here VCS as being equal to Vs over RC divided by S plus 1 over RC and VC0 divided by S plus 1 over RC, where the time constant is equal to RC. RC is known as time constant. Now, just like the previous RL circuit, one of the term is dependent on voltage and the other term is dependent upon the initial charge. So what will this be known as? Zero state response. And what will this be known as? Zero excitation response. On taking Laplace inverse and substituting the value of Vs depending upon which kind of input has been applied. As for example, Vt is a DC voltage, VUT, such that its Laplace transform is equal to V over S. So when we put the value of V over S comes in the denominator and V over RC is in the numerator, and we can take the partial fraction. One of the part will be A over S, another is B over S plus 1 over RC. And this VC0 over S plus 1 over RC remains as it is. Fine. The value of A and B can be determined by the usual method of V over RC divided by 1 over RC is V, and V over RC over minus 1 over RC, substituting the value, is minus V. Now we take the Laplace inverse. So VCS is, after replacing the value of V over S in these terms, we take the Laplace inverse and we get these expressions. VCT is VUT minus V e raised to the power minus T over RC, and VC0 into e raised to the power minus T over RC. And obviously UT is there with each of these terms. Which is this part? It is dependent on voltage V. And which is this part? Dependent on initial condition or a zero state condition, VC0. This gives the zero state response, and this one gives the zero excitation response, which has been plotted as before. Zero excitation response and zero state response. And these two are combined together. This and this combined together, you get the complete response. One thing can be compared. These expressions, these diagrams are exactly the same as we had for an RL circuit. I just bring that sheet again so that you can have a comparison. Zero state response, zero excitation response, and complete response. And now we have zero state response, zero excitation response, and here complete response. So what inference are we drawing from this? If we have an RL circuit, then take the current IT and determine it. If you want any voltage, you can very well establish after determining the current. Similarly, when you have to find out the response for an RC circuit, take the output response of the voltage across the capacitor, write down the equation pertaining to it, and thereafter, if you want some current to be determined in the circuit, you can very well find out IT as being equal to C dVc over dt. By this expression, you can get the value of IT as well. Thank you.